So for this part, we're going to look at the alternating series test. This is a test that allows us to see if we have an alternating series, whether or not the series is convergent. So the test just needs to pass two conditions, and if these two conditions are satisfied, then the series is considered convergent. And we're going to look at an example to see how this works in practice. So for this example, we're going to have our series S equal to the sum from n equals 1 to infinity of -1 to the power of n minus 1 times 1 over n. So then this 1 over n is going to be our b of n that's here from the definition. And this is just going to be equal to 1 minus a half plus 1/3 minus a quarter plus 1/5 and so on. And so to see if this series is convergent, we first have to check the first condition, which is this one. It's bn plus 1 smaller or equal to bn for all n. And this just means that the term bn can't increase from one term to the next. So here bn is 1 over n, and we know that that's just 1 and then 1/2 and then 1/3 and then 1/4 and so on. So that's always decreasing. So we know that the first condition is satisfied. And then the second condition is that the limit of b of n as n goes to infinity has to be 0. And so here b of n is 1 over n. So all we have to do is limit of n as n goes to infinity of 1 over n, which is equal to 0, because as n goes to infinity, 1 over n goes to 0. So also in this case, the second condition is satisfied. And since both conditions are satisfied, we can say that S is convergent thanks to the alternating series test.
Hi, I'm Umberto. Today I'll explain the alternating series estimation theorem, which allows us to estimate the error when approximating the sum of an alternating series. When working with an infinite series, we often approximate the sum by calculating a partial sum, which we denote as S sub n, as shown here. The full sum of the infinite series is represented by S, as shown here. Since we cannot compute all infinity many terms, our goal is to understand how close S sub n is close to the actual sum S. The difference between the true sum and the partial sum is called the error or remainder, and we denote it as R sub n, which is equal to the absolute value of S minus S sub n. The alternating series estimation theorem applies to the series of the form, as shown here, where B sub n is greater than 0. This theorem holds true if two conditions are satisfied. Number one, the sequence B sub n is monotonically decreasing, meaning that B sub n plus 1 must be equal or less than that of B sub n. Two, the terms approach 0, which means that the limit as n approaches infinity of B sub n is equal to 0. If both conditions are met, the series converges, and the absolute error when using the nth partial sum satisfies this statement, the absolute value of S minus S sub n, which must be less than or equal to B sub n plus 1. This means that the magnitude of the error is no greater than the absolute value of the first omitted term, often referred to as the first neglected term. To illustrate this theorem, consider the alternating harmonic series. Suppose that we approximate the sum using the first four terms, as shown here, which is equal to 0.5833. The next term, which we do not include, is b sub 5, which is equal to 1 over 5, which is also 0.2. According to the theorem, the error in our approximation is bounded above by this value, also shown as S minus F sub 4, must be less than or equal to that of 0.2. This tells us that the actual sum lies within 0.2 units of our approximation, meaning that the true value is somewhere between 0.3833 and 0.7833. In fact, the true value is approximately 0.6931, and as predicted, falls within that range. To summarize, S sub n is a partial sum, or approximation. S is the total exact sum of the series. R sub n is equal to the absolute value of S minus S sub n, which represents the error, and the theorem guarantees that S minus F sub n must be less than or equal to that of B sub n plus 1. In short, if a series is alternating with positive decreasing terms that approach 0, the alternating series estimation theorem provides a simple but powerful bound on the error. This makes it a valuable tool for estimating the sum of a convergent alternate series with confidence.
Okay, so now we're moving to a new topic that's related to the prior one. absolute convergence and conditional convergence. So let's start with a definition. A series is called absolutely convergent if the series of absolute values is convergent. We'll see what that means through an example. Let's take the following series. The cosine of pi n over n to the fourth power. As you can see, it's an alternating series because cosine of pi is -1, cosine of 2 pi is 1, cosine of 3 pi is -1, and cosine of 4 pi is 1, etc. So it alternates. So to determine if it's absolutely convergent, we must place each one of these terms in an absolute value. So each one of these must now be positive. So this one becomes 1 over 1 to the fourth plus 1 over 2 to the fourth plus 1 over 3 to the fourth. All of these become positive. So to determine if it's absolutely convergent, we must determine if this new series is convergent. So recall P series. P series is a series with this form, 1 over n to the p. And if p is less than or equal to 1, the series diverges. If it's greater than 1, it converges. Here, p is 4, and since 4 is greater than 1, this series converges. So since this original series over here, when placed in absolute terms, converges, we can say that it is absolutely convergent. Now that we know what absolute convergence is, let's look at conditional convergence. A series is called conditionally convergent if it is convergent but not absolutely convergent. That is, if a series converges but the absolute value of it diverges. So let's see what this means through another example. Take this series, -1 to the n plus 1 over the fourth root of n. As you can see, it's also an alternating series because the signs alternate and it's a series. So to test if it's absolutely convergent, we must place these terms in an absolute value. So all of these become positive. The fourth root can be written as 1 over 4 as an exponent, so let's rewrite that. So as you can see, all of these become positive. So to determine if it's absolutely convergent, we must determine if this form of the series is convergent. So recall the P series we mentioned in the previous example. If P is less than or equal to 1, it diverges. If it is greater than 1, it converges. Here, P is 1/4, as you can see. And since 1/4 is less than 1, this series diverges. So as we can see, it is not absolutely convergent. However, as mentioned, a series can be conditionally convergent without being absolutely convergent. So let's determine if it's conditionally convergent. So we know it's not absolutely convergent. So how do we determine if it's conditionally convergent? Well, as we explained previously in this video, we can apply the alternating series test. So if it meets these two conditions, then it is convergent. So let's apply these two conditions to our case. An alternating series, as we explained before, can be written in this form, -1 to the n plus 1 of b over b sub n. So how does this apply to our case? Well, this is a series I gave as an example. So this part is a numerator, therefore b sub n is 1 over n to the 1/4. So equals b sub n. So the first condition is b sub n plus 1 less than or equal to b n. So let's apply this to this case. So b sub n plus 1 would be b sub n plus 1 to the 1/4 would have to be less than or equal to n to the 1/4. And if we analyze this, this condition is true. We can see it through an example. Let's say n is 1. It'd be 1 over 2 to the 1/4 is less than or equal to 1 to the 1/4. And this is true because this number is greater than this number, so therefore this number is larger than this number. So first condition is met. Let's test for the second condition. So b sub n, as we saw, is 1 over n to the 1/4. So we want to know if the limit of that as n approaches infinity is 0. And this is true because as n approaches infinity, as this number gets larger and larger and larger, this number approaches 0. So therefore, condition 1 and 2 are met, and therefore the series is convergent. So since it's not absolutely convergent, but the alternating series itself is convergent, we can call it conditionally. One last idea you should take into account is the following theorem. If a series is absolutely convergent, then it is convergent. So if we go back to the first example when we determined that it was absolutely convergent, we could say that that series is, by this theorem, convergent.
After learning about alternating series and absolute convergence in chapter 11.5, we now go on to chapter 11.6, where we get some techniques of learning or finding out the convergence of a given series. So the first topic of 11.6 is the ratio test, and this has three possibilities. With the motivation of determining if a series converges or diverges, we use this technique. So the first possibility is if we take the limit as n approaches infinity of the absolute value of the nth plus 1 term over the nth term, and that is less than 1, we know that the series is absolutely convergent and by definition convergent. The second possibility would be if that limit is greater than 1, and then we say the series is divergent. And lastly, if the limit is equal to 1, this test is inconclusive and we'll need to use other techniques we have learned previously. So let's go on to examples to find out how to use the specific technique. So let's test the given series for absolute convergence. So we set it up as the absolute value of the nth plus 1 term over the nth term. We get the following expression from which we can cancel the -1 to the exponents simply because we have the absolute value. Then we get the following expression right here. And from knowing about power rules, we know that 3 to the power of n plus 1 over 3n is just 1/3. And we get the following expression. And when we take the limit as n approaches infinity, we see that this expression right here approaches 1/3. Since 1/3 is less than 1, we deem this series absolutely convergent. Now let's go into the second example, which would have the second possibility of the ratio test. So we have the given series that we need to test for convergence. We set it up in the same way, only now we get rid of the absolute value since all the terms are going to be positive in this series. And after doing some expansion of the exponents right here and the expansion of the factorial, we can cancel out some terms right here, and we get n plus 1 over n to the power of n, which this expression, when simplified to this and taking the limit, approaches e as n approaches infinity. And since e is greater than 1, this series is divergent. We could have also used another technique just by testing for divergence, and we see that this series does not approach, the sequence does not approach 0 as n approaches infinity, and therefore we see that the ratio test agrees with that. However, it is also a great possibility, and it's very easy to use to test for convergence. Lastly, let's have two final examples about when the given series or the limit of the ratio test is inconclusive. So we take the first series right here, and we see that it yields n over n plus 1, which as n approaches infinity, this expression approaches 1, which we say the test is then inconclusive. However, we know that this is a harmonic series, therefore it is divergent. So this is an example where we would have to use some other knowledge or other techniques we have learned about to find out the convergence of a given series. Now, if we look at the second example, we have something similar where we get n over n plus 1 to the power of 2. And as n approaches infinity, this expression approaches 1. We again see the test is inconclusive, and thus we can't really determine the convergence of this series. However, we do know that there's a p series with p greater than 1, and therefore this series is convergent. This being the root test, if you want to know more about the theorem behind it, please come to my office hours on Saturday, 21st. And now Faye will tell you about the second part of chapter 11.6, which is the root test, which is really helpful in about finding the convergence of a series when there's powers to the power of n involved.
Is Faye, and I'll be explaining the root test. So let's start off with what is the root test. So it's basically a method that we use in order to figure out if an infinite series adds up to a finite number or not. How does it work? So the first thing is that we have to look at the infinite series itself. Then we have to take the ninth root of the absolute value of the general term. So basically we have to look at the n. And once we solve, we have to look at the value of the n. So if it's less than 1, then the series converges. If it's greater than 1 or equal to infinity, then it diverges. And if it's equal to 1, then it's inconclusive and you have to do another test. So let's take an example right now. So this is our example. The first thing we'll be doing is taking the nth root of the value of an. So an here is equivalent to 1 over 2 or half the power of n. So in order to take the nth root of the absolute value, what we're going to do is this. We take the absolute, we put n here, and then the absolute value of half the power of n, absolute value, equals to 1 over 2. Then we're going to take the limit as n approaches infinity. So L equals to limit n to infinity, which is equal to half, because there's no x value for you to plug in the infinity. So since L is equivalent to half, which is less than 1, the series converges. So that's it. So the root test basically is that easy. It's a quick way just to test the convergence or divergence of a series. So thank you for watching and I hope you understood.